Hello, and welcome to the second half of Project 3.2, also known as the CHUMP, for Cheap, Homemade, Understandable, Minimal Processor. This is Feinberg's code currently running. It adds one, then repeats this function over and over again until it overflows. This is the program ROM that was featured in the last video. However, there's been many modifications made. First of all, a switch was added to change between two separate programs. Feinberg first, then my personal code. Second of all, the outputs, instead of going from the program ROM to a 10-second LED, now go to the multiplexer for the low 4 bits, and the control ROM for the high 4 bits. This is the control ROM connection right there. Now, if you look at the lowest of the 4 high bits, it connects to the multiplexer. This is because it's used as a pseudo controller. This is the control EEPROM, very similar to the program EEPROM. The highest 4 bits of the program EEPROM control the control EEPROM. The highest 4 bits of the control EEPROM are S3 to S0, and they connect as such on the ALU. After that is M and CN, or mode and carry. These also work with the ALU. The lowest two, the second lowest is the accumulator and connects as such. And the final lowest is read-write. It connects to the address, which connects to the accumulator. This is the ALU, the arithmetic and logic unit. It's the brain of the CHUMP. It takes the B operand from the multiplexer, as seen in white, and compares it to the A operand when 2 operands are needed. The controls, of course, in blue, and they come from the control EEPROM. Now, the green output is the same as the green input. That's because the output goes into the accumulator and the accumulator files back around. This is so that values in the accumulator can be modified with B, the input from the multiplexer. If you look on the top right, you'll see a resistor and an output. That goes all the way down to the program counter, where it allows the goto function and the if0 function to work. This is the accumulator. It stores the value of the ALU. It's technically a data register, but on old-fashioned computers like this one, they're called accumulators. It stores the value of the ALU inside of it when a clock is pulsed. It then outputs to the RAM. Of course, the output to the RAM doesn't work anything unless the RAM is supposed to be storing something, which of course happens to the address. That's the purpose of the ALU. It's also generally treated as the main output, as you can see by these red LEDs here. This is the multiplexer. It selects between the input from the program EEPROM or the RAM NOT gates. This is what serves the input for the B and the address register. It's quite important. This is the address register. It takes the input from the multiplexer, as seen in white, and outputs to RAM, as seen in red. There's also one control line coming from the control EEPROM, which selects read-write in the RAM. It gets stored when clock is pulsed, as seen by the blue in the upper left. It also outputs to several LEDs, although this does cause some weird issues when running longer sets of code. Due to its namesake, it's quite easy to infer that the address register stores the values for RAM that you want at a later moment. This is the RAM. It stores inputs so that can be used at a later moment, later on in the instructions. The inputs come in red, and these are the addresses. The data inputs, however, come in green. These are only used when writing data to the RAM. However, there's one quirk. The RAM's outputs have to be inverted. It's a weird quirk. I mentioned it in my writing. Now, this then, of course, connects the accumulator, and the output of the NOT gate, which is actually the output of the RAM, connects to the multiplexer where it can be selected. Here's my code running on my machine. I had to remove the RAM LEDs and the address register LEDs, as they cause weird bugs the longer the code starts to run. I don't know what causes this. This code is calculating the Fibonacci sequence. Here's the second number, 2, 3. It'll then store to separate locations in RAM, and then 5. Of course, this calculates the Fibonacci sequence. This is limited to a maximum of 15 because it's 4 bits, therefore is not particularly useful. Thank you for watching. I've been looking forward to this project ever since grade 10. To be frank, it hasn't disappointed. This is probably my favorite project of all high school. It's amazing. See you, gents.